Now let's take a look at the networking components inside our Nova environment. It's one thing to have a compute platform. It's not going to do you much good if it can't speak to the rest of the world. Inside our Nova networking, we have the traditional virtualized networking features that you'll see in pretty much any virtual or cloud platform. We provide layer 2 and layer 3 services and DHCP service into the environment so that our instances have access to all of those different boundaries and can be bridged into the outside world. There's different networking models which are deployed using the Nova networking platform. These are known as the flat networking, flat DHCP, and VLAN manager model. In a flat networking model, we have a dedicated subnet of IPs, and each IP address is injected into the instance at boot time. The next one is flat DHCP, which is much more common, I find, where we actually allocate an IP address and it's picked up using the DNS mask service and is deployed into the DHCP as the instance boots. The third option is VLAN Manager, where a tenant is actually allocated a VLAN and an associated IP address. So that's for the more deeper layer 2, layer 3 boundaries within the tenant. And then to get to the outside world, we can use floating IP addresses. This is an externally facing IP address that can be mapped against a nested instance in order to provide it external access. We can provide external access through the different flat models and the VLAN models as well. It gets a little confusing, so maybe we should take a look at it in graphical format so that it'll make more sense. Our first model is a single flat model. This is where our cloud environment is provided with a subnet. In this case, it's 30.0.0.0/22. There's an external gateway of 30.0.0.1, and every instance that's booted, regardless of tenant, is provided an IP address in this shared net environment. So you'll notice that tenant A and tenant B, each of their VMs has a common IP address range in order to access themselves and externally. This is a very simple model and most common in lab environments. Next up, we get into something a little bit more complex, but really it's just a little bit more granular. In the multiple flat model, we have multiple subnets that are presented to our tenants. Each, again, is just a layer 3 network, so 30.0.0/24, 30.0.1.0/24, etc., etc. Underneath, any of the tenants can map to any of these networks. So tenant A, you'll notice, has a VM1, which is on the shared net 1. And then VM2 for tenant A in the middle is allocated onto shared net 2. There's really no rhyme or reason to how those end up, but this allows us to expand that IP range. But again, using the same simple flat model. And then each range is provided a gateway to be able to map to the outside world. Next, we have the flat and private model. This is going to be something that's much more common in cloud environments. Not only are they provided an external range of IP addresses with the 30.0.0.0/22 in the shared net range, but underneath that, each tenant is provided its own private network. So what's that for? Well, imagine that we wanted tenant A to be able to have what we call east-west traffic. This is traffic that's transmitted between machines, but doesn't necessarily have to bridge to the outside world. It can at the same time. We can have shared environments between the private and shared environment. So you'll notice on tenant A that each of their machines has both a 30 address and a 10 address. So each instance has 2 NICs and a specific IP address in each of those ranges. There may be certain traffic that they only want to be transmitted across the 10 network for privacy. And then all external facing traffic traverses the physical router using the 30.0.0.1 gateway from those 30 addresses. Tenant B there only has one machine, which is nice and easy. Tenant C has a really cool case. Tenant C has VM1, which is externally facing on 30.0.0.5, and is given a management or private network address of 10.0.0.2. But their second VM is only provided access to the private network. Effectively, it only has east-west access to VM1. VM1 can see outside and inside. This is a great model where you're going to see sort of N-tier applications where those middle tiers don't need to be externally facing. We can get even more granular, or depending on how you look at it, more complicated, by providing a provider router. So this is an internal router that maps against an external gateway. We still have that same external, what we used to call shared net, which is 30.0.0.0/22. Same external gateway, 0.1. But we've provided 0.2 as a provider router gateway. So this is a nested router, and inside each of our tenants is given another private IP range so that they don't have to have an external direct connection. You'll notice on tenant A in the upper left-hand side that each VM has both a 10 address from the private net as well as a 30 address. Those 30 addresses are allocated using the floating IP addresses that we talked about in the earlier slide. Then in tenant C, we have the same thing we saw in the previous slide. Tenant C has VM1, which has both external and internal access to their private network, and VM2 is only mapped against their private network, so it has east-west traffic access into VM1 over the shared private net. But there's no risk of external access because there's no externally facing IP address, and it's nested behind that provider router. And now we're getting into even more granular control. This, again, is becoming the sort of typical you'll see in an IaaS provider. You would see the private network only, and each tenant is given its own specific nested router. This is for more granular control and logical separation for security reasons and for just general network practices. So tenant A has their own specific router, which has one gateway address into the external network, and that's 30.0.0.2. Tenant C router has 30.0.0.3. Now, you're going to notice when you look at the tenant IP addresses, this is where it gets really exciting. Take a look on the upper left-hand side, tenant A VM2. On their private range, they've been given 10.0.0.3. Now, slide over to the right a little bit, and you'll notice that tenant C also has 10.0.0.3. Because they've been provided with separate tenant routers, you can have overlapping IP ranges. This is the magic of cloud networking. We no longer have to have massive topologies laid out so that each tenant gets their own subset with variable length subnet masks. They can each be just assigned a bunch of Class C addresses like 10.0.0.0 and 0.1, and they can be completely overlapping because all of the external access is provided using the floating IP ranges. But there's a lot of flexibility that you can see with this. We always joke about the phrase, "the rumors of my death have been greatly exaggerated." And this is very true about Nova networking. Earlier on with the Havana release, there was chat about Nova networking being deprecated. What that means is that they were going to actually cease development against the platform, and they were going to move to the more fulsome OpenStack Neutron, which was then called Quantum. OpenStack Neutron was a very flexible and powerful networking platform. But the migration over from Nova networking in the traditional layouts into the Neutron environment required a lot of care and feeding. And luckily, the magic of community came true. So the community spoke, and we realized there were a lot of customers out there using traditional Nova networking. As a result of that, more community members were willing to continually commit to Nova Networking to grow and expand it in order to meet both current and possibly expanding needs down the road. So as a result, Nova Networking lives on. Well, now that we've sort of touched on OpenStack Neutron, maybe it's a good time to jump into that.